이건 또 뭐야?
Alright.
Songs like this, I sometimes feel my title's a bit too. Yeah. So this talk is based sort of on my PhD thesis, and yeah, these really are sort of disasters. They're strong sort of negative results where characterizations go spectacularly badly. I want to cover a lot for sort of more general audience. So it's mostly going to be big picture, but I'm happy here to go into more detail with them. If anyone has questions? Okay. So say you have a set of real vectors in real vector space. One way to describe sort of their inherent geometry is by giving the collection of independent subsets of these vectors. So this collection of independent subsets doesn't capture sort of everything. So if you do sort of row operations, consider the vectors as matrix, or if you sort of scale the vectors, you will preserve the set of independent subsets. But it does capture a lot of sort of the geometry that we do care about. And this is sort of clear if you think of these as projective coordinates. And because I don't want to always draw sort of, or give the independent sets, I'm going to often sort of draw it as a diagram geometrically. Where elements on a point, you have a maximum of, there's no two elements on a point that are linearly independent. And there's no three elements on a line that are linearly independent, and so forth. So if you're thinking about this as projective coordinates, or if you have a component vector in common for all the vectors by sort of row operations, the remaining will sort of be the affine coordinates. So I'm just going to do sort of another example. Make this drawing shorthand clearer. I'm considering vectors u, v, and w in R3, and I've considered various sums. So they sort of fix in affine plane R3, and I scale all the vectors so that they lie on this plane. The lines that I described really sort of are lines in this drawing. And you can sort of, if the drawing is small enough, you can determine what the independent subsets are. So sort of this drawing is the corresponding, we'll describe, linear independence for over the reals. Okay, so that's actual linear independence. So now, instead of actually having sort of coordinates, what if I just let I be a collection of subsets of some sort of ground set, and have this collection establish what the independent subsets are? So then the question is, when can you represent a pair of the ground set and the independent subsets with a set of real vectors? When is this actually correspond to linear independence in a real vector space? So, for example, if I give you some drawing, can you have vectors where this is the appropriate sort of linear independence relation? So if 2 points, if we have 3 points on the same common line, they're not linear independent. So can we answer this? And in general, if we're given some independence collection of a ground set and independent subsets, can we characterize when it has a real representation? Okay, so first, some immediate necessary conditions one will notice. Well, you can't have no independent subsets. The empty set is always going to be independent. And if you have an independent subset, or if you have an independent set, then any subset will also be linearly, will also be independent. I shouldn't say linearly independent. Okay, so these are sort of natural conditions, and in fact, when this is the case, pair EI is called an independent system. Also a general simplification complex. But these aren't sort of sufficient. Two drawings here. The one on the left should be sort of clear. I have 4 points and 2 lines. The one on the right, you should think of it as having sort of all the points, lines, and planes that one would expect from sort of the 3-dimensional drawing, except one distinction I'm going to make is that these 3 points on top are not on a line. They are linear, or they are independent. So you can think if you have, if you can assign sort of real vector to each of the points so that you have the appropriate sort of, so it is represents this independent system. And on the left, well, it should be sort of clear because you can't have 2 lines that intersect at 2 points. And on the right, these 3 points pose issue. So in both cases, it can be sort of summed up as having a maximal independent set that is sort of smaller than it should be. So on the left, if you add either of the 2 points, you get a line, so it will no longer be independent. And on the right, if you add any of the points on either of the sides, you get a plane sort of corresponding to that side. So the issue here is you have a set that's independent, and it's smaller sort of than some other independence set. So from linear algebra, think of sort of, well, if you have a linear independent set and a larger linear independent sets, you can always sort of add something that's not in the span of the original ones. So we'll add this condition, and that will get rid of both of these sort of examples. This is also sort of a natural condition. And note that, it does get rid of both these because here x's are collection of points, and in both cases we have a larger independent subset that can't sort of be extended. So when these 3 conditions hold, systems called matroid. So, if you think about it, this sort of collection of conditions is still not sufficient. So, for example, the Vamos matroid doesn't have a real representation. So here I have 8 points, and I have sort of 4 lines consisting of a pair of points, and any sort of pair of 2 lines is going to lie on a plane, except sort of the one on the far left and the one on the far right. And see why this is not sort of re-representable. Because the lines B and C sort of are on a common plane, they'll have an intersection point. So if this has a re-representation, we'll assume this has a re-representation and show that this is impossible. So if this is a real representation, because B and C lie on a common plane, they'll have an intersection point in the real, in sort of the real vector space. And because of the earlier non-matroid I gave, that sort of looked like a pyramid. A will have to contain this intersection point. And similarly, sort of the same sort of non-matroid, we're going to have, D is also going to have to contain sort of this intersection point if this is a real representation. But now, A and D would both have this intersection point, but they're skew sort of according to formulation. So this is impossible. You can't have 2 lines containing the same point and be skewed in a sense. So this is not real representable. So we could add a condition to get rid of sort of this obstruction, and we might ask sort of if we can sort of continue adding conditions. So can we add a finite number of conditions to sort of get rid of obstructions and characterize real representability? If I have a finite number of conditions, I can just really write them as one condition. I can just, say I1 and I2 and I3. That's, a single sentence for characterizing matroids. So if we ever have sort of finite collection, we can write it as a sentence. So having a finite axiomatization of real representability is having a sort of sentences language. I have sort of said what real representability is. It is having a set of vectors in a vector space where linear independence. But that's sort of the wrong language, right? We want to limit ourselves to only talking about independent sets. We don't want to talk about vector spaces and the actual linear independence. So we want to limit our language to sort of talking about when sets are independent and sort of elements, subsets. So note the third condition, for example, already sort of talks about size. And we think about this problem, but size is not really a set condition and doesn't talk about independence. But we can, in fact, sort of replace this third condition with sort of something in the language of sort of independent sets. And you can write this precisely with sort of logical language. And this is sort of independent set language, MS. So Mayhew, Newman, and Whittle showed that there is no sentence in sort of this independent set language that characterizes real representability. And sort of there is no logical approach where you limit yourselves to a natural language. Okay, so that doesn't work. Another thing one might consider is just giving obstructions. So we have the Vamos matroid, for example. What if we disallow certain matroids? And we want to sort of look at minimal obstructions. We could have added certain things to the values, but we only want to care about minimal sort of obstructions. And matroids sort of have a minor operation I'm not going to go into. But Mayhew, Newman, and Whittle also showed that, in some sense, the obstructions to real representability are just as complicated as the real representable matroids themselves. So every real representable matroid is contained in some minimal obstruction. And yeah, this just is very bad, because then, you know, instead of giving the minimal obstructions to a class, you might have well just given the class in the first place. And final sort of type of characterization I'm going to talk about is from sort of a complexity theoretic standpoint. What if we want to show, or have an algorithm, non-deterministic algorithm, or just to show that something is or is not real representable? And this also goes sort of badly. You can't show in sort of using a polynomial number of sort of independence or dependence evaluations that real representability is or is not the case.
When you say something is polynomially certifiable, that means you use this oracle, independence oracle?
Independence oracle. And I mean in the number of elements. Yeah, so independent oracle. Exactly. Yeah. So yeah, if anyone wants clarification on anything, just please ask. This is, yeah.
Real representations, does it ever involve, do you have to use properties of real numbers, some crazy irrational thing, or is it always essentially just
yeah, that's essentially what I'm, the key idea behind sort of all of these are using things that aren't representable over anything. It's using something that doesn't correspond to linear independence in a generic sense over any field. So the values, for example, you could do the same argument over any vector space. So to show each of any of these, it was really using sort of an actual obstruction to linear independence in general. I'm glad you asked that question. So Nelson showed that as you go to infinity, the proportion of matroids that are representable over some field tends to 0. So with how everything was proved, that makes sense. We're using something that dominates the class of matroids in general to so it's possible, it's conceivable at this point to think that maybe the characterizations go wrong because just to characterize linear independence is difficult.
So this is for a fixed field, the proportion tends to 0, or for all fields?
For all fields.
Okay.
So asymptotically, almost all matroids are not representable over any field. So maybe that this is the issue. So what if we restrict to sort of considering characterizing real representability when we know that it does actually correspond to linear independence over some field? And we can, let's do even stronger than this. Let's just look at complex representability, because we know if something is real representable, it's going to have to be complex representable. If you have projective sort of coordinates over reals, it's also complex. So what if we know we have sort of a complex collection, a collection of complex vectors where our independent system is described by this collection? So the answering is that we still have, everything still goes wrong in essentially the same ways as before. Even if we're only looking at complex representable matroids, characterizing real representability is still bad in each of the fashions.
I'm sorry, I think you already answered the question, but when you say that determining that it's real representable is not polynomially certifiable, what is the computational model? What are you you've got some kind of oracle to determine it?
Yes.
So you got like certain queries you can make, but you're not using like real arithmetic or something, or what's the or does it matter?
So when I say polynomially certifiable, when I say certify, given sort of a ground set and a collection of sets that are either independent or dependent. So you give me a ground set, I'll tell you these are independent, these are dependent, and that can possibly determine the whole matroid. It's also possible it could rule out everything that's not real representable.
I see.
So it's the number of things you either have to certify to be a dependent or independent set. Or the collection of things you have to sort of check to rule out.
I see. So it's not like somehow I'd imagine that you're saying that if you give me the description of a matroid and a polynomial sized circuit, then in polynomial time, or I mean a polynomial sized certificate, then so if I know all of the I know all the independence relations, and you tell me the answer, then I can't, like you give me a real embedding, for example, then could
like NP problems.
Yeah, it's in some sense you can think of, you already know the answer. So can you prove?
Right. So here's a question. Let's suppose you give me all the, or you are willing to tell me all the independence relations, and you give me an explicit embedding of the points that you claim satisfies these independence relations. Could I check in polynomial time to see whether that you're given?
That's sort of one of the things you're given, so you'd have to verify that representation is a representation that has sort of, you'd have to check. Like exponentially many. Like there are exponentially many sort of subsets of the ground set, right? So
I couldn't find like a polynomial size structure inside where if I just knew that these guys were independent and I go, these are dependent, then.
There are some interesting questions I still sort of want to think about from this perspective. Like if you have a complex representation, maybe you can do a combination of certain, but at this point it's only asking sort of, if I have, I just know it's complex representable and you're given independence,
I know it's complex representable and I'm given access to know whether I can query certain subsets and say, are they?
And in fact, I'm like, you can't prove to me, right? You're querying, I mean, if you're thinking of it algorithmically.
There's an exponential amount of data about them.
Yes, exactly.
And so we're talking polynomial on the ground set.
Yes.
Right. Potentially there could be many inequivalent representations, right?
Yeah.
So if you have characterization of the representations, then it may be possible to say, okay, if I have a representation for potential representation, you can maybe under certain situation you hope to convert it to another representation where you then compare. But in this real case it doesn't work.
Yes, no, I'm just thinking of having independent system in general.
Yeah.
Oh yeah. So to check that something is a representation, you'd still need exponential many. But if I, yeah. So one of the open questions, for example, is if I tell you this is a complex representation,
Yeah.
can you
Determine whether it has a
exactly?
Yeah.
But to check whether or not it is actually a complex representation would require more. Hopefully it will be clear when I do one of the actual constructions. I can go into more detail. When we see the construction, you can pick my brain. Yeah, but we'll have other constructions. We'll also sort of do the previous case, right? Just because if you have the n logs. Yeah, so I can ask questions then if it's clear. Okay, so now we're using such that thing. Now we want things that are complex representable but not real representable. So to get sort of appropriate analogs, we need to use properties of the reals now that are true, like conditions that are satisfied over the complex numbers but aren't over the reals, to sort of have constructions that are complex representable but not real representable. So we need to be able to encode sort of algebraic conditions in a geometric structure, and we'll use sort of these geometric conditions to have something that is complex but not real representable. So the way we're going to sort of encode algebraic conditions is going to think of values as sort of points on a line, where we have sort of a fixed 0 and a fixed infinity, and then our values are going to be sort of any value is going to be sort of on that line between 0 and infinity, with sort of and if we have a representation, we'll the representation will sort of correspond to the what that value should or could potentially be. And we're going to add sort of gadgets that enforce algebraic relations of sort of these points in the line. And we're going to sort of be able to combine gadgets by amalgamation, sort of gluing across a common line. And this idea of sort of encoding values in a line and having sort of geometric gadgets actually dates back to von Stout, 1857, and what he called sort of algebra of throws. And I'm not going to sort of give all constructions, but I'm going to give sort of nice example. So here I'm going to give sort of the gadget for non-trivial addition. I'm saying non-trivial here because we have x and y that are different, and that sum to a different value that is also not zero. And the reason for this is because when we have points on the line, well, we don't want those points, the two values aren't on the same point, so they have to be distinct values. If we're giving a matroid, we're saying that the value x and y are on two different points, so they're sort of distinct values. And we can look at sort of how to do if there is some degeneracy. You just combine points. Okay, so how does this sort of enforce addition on a line? So by sort of row operations and sort of scaling, we can assume sort of you have embedding sort of where point infinity is in a sense at infinity, and the last two coordinates are in some sense the Cartesian coordinates one would normally expect. And if you want, you prefer, you can just look at the vectors I've given, and instead of doing this sort of Cartesian or Euclidean geometry, you can think about how spans should meet. Okay, so let us look first at this point, and a sort of vector that corresponds to this point. So either sort of think of the span of these two vectors and where they intersect, these two, or sort of from the Cartesian perspective, these are similar triangles. So here the distance between 0 and x is x, and sort of by a similar triangle argument, the distance on the bottom length should be 2x. Or you can find that the an appropriate vector, sort of up to scaling, so the first coordinate is 1, is sort of as I've written. And you can do same for y. And now, that's sort of the final point, if we're looking at how these two, the span of these 2 points should meet the span of this. When you add them and divide by 2. So we get precisely sort of what I said we would. So this does enforce addition.
So basically, you want to map the elements of the field to the points on the space so that the algebraic operations can be realized by the intersection of lines.
Yeah.
Like a construction.
Yes. So so I'm having values on just a single line at this point. So when we consider a representation, you can think of a representation as sort of evaluating that point as whatever value it should have. Sorry, I understood your question. Did I answer that clear?
I think so.
And if we have sort of degeneracy, if x equals y, you just sort of have the incidence. And you can even sort of go further and have a further degeneracy where what if x plus x is 0? So this is sort of the matroid that would enforce that condition. But over the reals, you don't have any sort of non-zero element that sums up to 0. So this matroid is not really representable. It's only representable fields with characteristic 2. And we draw it, might be more familiar to some of you, and it is the earlier example I gave. It's a Fano matroid. Okay, so this is one way to enforce algebraic conditions on a line. I'm going to sort of talk about a different way to encode or to enforce sort of algebraic conditions on different lines. And this will sort of be based on determinant here. If you just expand determinant, there will only be 2 terms, and because of this, we just show that that collection of vectors is linearly dependent precisely when sort of the corresponding values multiply to 1. So if you're thinking sort of what the matrix would look like, you'd have an independent set of size n, v1 to n, so this is a basis in the matrix sense, where any element will lie between sort of, cyclically ordered basis where any element lies in the span of sort of 2 consecutive elements. And sort of span of any of these 2 consecutive elements is going to sort of be a line, and we'll think of sort of, again, values on lines. And if you take an element from each of these lines, a transversal of all of these lines, you have the dependency precisely when sort of the corresponding values multiply to 1 again. So this is a way to sort of enforce a collection of multiplicative relations. So, for example, for an integer n is 2, if you consider sort of a system which says that the order of alpha is n. No power of alpha less than n is equal to 1, but alpha to the n is 1. So we can encode this sort of, this rule like matroid omega n, where sort of have this collection of dependent transversals. So this dependency does ensure that the values the elements, the points in each line that we've labeled 1 are sort of indeed 1s, sort of up to row operations. This collection sort of here, we have 1 for each of the other lines. They ensure that the alphas are in fact sort of the same value. And the final one gives that alpha to the n is 1, because we have n alphas, and this dependency ensures that alpha to the n is 1. And the fact that we have no other dependent transversals, specifically no dependent transversals that contain sort of fewer alphas, means that no smaller power of alpha is 1. So, because you have roots of unity for sort of any integer n in the complex numbers, these all have complex representations, but the only one that has a real representation is omega 2, because s and minus 1 are the only real roots of unity. Okay. So now we actually have an example of a matroid that is complex representable but not real representable. So now I'm going to see how we can use this to sort of have some bad, to show some of the characterizations of that. So I'm going to sort of use this example of a complex representable matroid that is not real representable. And the one thing you're going to use, I'm just going to claim it, I'm not going to prove it, but we can check. if you remove an element of this matroid, then you do have a real representable matroid. You have some representation in reals, real vector space. And the idea we use is that if we pin down this missing element, sort of, if in some sense, if we can point to where it should be in sort of span sense, the resulting matroid cannot be real representable. Because if it was real representable, we could retrieve the missing elements and we get our omega 4, which we know is not real representable. So first, we sort of see how you can use this to show that any real representable matroid is contained as a minor in a minimal obstruction, that is complex representative. And the idea is for sort of a real representable matroid, you can construct a complex representable matroid that doesn't contain alpha 4, but with elements that point to sort of these missing elements of alpha 4. And you can show that this is, one can make this to be sort of a minimal obstruction, so this would be a extreme minor. So this, yeah, is how you can show that the minimal obstructions are at least as bad as the guess themselves. You can also sort of use this idea to show that you can polynomially certify real representability. And the idea here is in sort of a higher dimension or higher rank in the matroid sense, we freely place a collection of elements or generically place sort of points. And the rank n here means that we need an independent set, or we have independent sets of size n+1, and to sort of to point to any element on sort of the line, we need n+1 elements. So because we've freely placed a whole bunch of sort of points in sort of this flat, there are exponentially many collections of elements that could potentially point to the element that was removed. None of them do, but one of them could. And if you don't say that, you know, this collection doesn't point to sort of the element we've removed, it's possible that, you know, the matroid you're giving me is not really representable because you are sort of pinning this missing element. So to actually show that this matroid is really representable, you need to ensure that you're not pointing to this missing element with sort of any of the exponentially many sort of subsets of size n plus 1. Okay, so these were both sort of things that went badly because I've used the construction. The two other characterizations go badly because of sort of more complicated algebraic systems. So I'm just going to give sort of the algebraic ideas. So instead of showing that something is real representable, what if you want to show that something is not real representative? Or, yeah, it's not really representable. So for an integer n, into the system, so we have w and x to n as sort of two different values, but we have their cubes are the same. So we have two distinct cube roots, which is impossible over the reals. Cube roots are unique in the reals. So this system doesn't have sort of real solutions, but it does have complex solutions. But to show that this system doesn't have real solutions, you just have to give me, these two polynomial size. It's sort of, easy to show or certify that it doesn't have a solution. So we'll want exponentially many sort of equalities or inequalities, and do this by sort of having dummy variable y, and we now have sort of exponentially many. We have words in x and y, and none of these products is w. But still, to certify that this does not have a real solution, you only have to give me the first two. It's easy to know which two are bad, or which two prevent a real solution from existing. So yeah, you can still sort of polynomially show, or constant show, that this has no real solution. So we need to hide or obfuscate which of these is sort of the inequality or non-equality that prevents a real solution from existing. And so for each additional sort of word of the product, we'll have AI and BI instead, and you don't know necessarily now which is which. So if you give me all but one of these non-equalities, it's possible that this non-equality is the one, if you consider, without loss of generality, you give all but the first one, then it's possible that in this case, AI is x for all I. So to show that this does not have a real solution, you need to actually give sort of exponentially many non-equalities, and yeah. You need to give all of them. Is that? So, strictly speaking though, this system isn't just purely algebraic. The last condition is just a set condition. So, we haven't talked about encoding sets in matroids, so we need to replace this last condition with an algebraic one. And we can do this by just having a quadratic that has this set as roots. And we'll sort of say what the quadratic is by just giving it coefficients, and we have relationship between roots and coefficients of polynomials. So we just give sort of these two relations to say that these two sets are, this pair of I and BI is equal to x and y. So everything before this sort of done on Swirl-like Matroid, and you can do this sort of using one-step constructions, and sort of the resulting matroid you get requires at least 2 to the n sets to show non-real representativity. Essentially because of what I was saying before, if you don't give sort of one of these non-equalities, then you have a real solution, where you've taken that non-equality you didn't give to be the non-equality that is actually the inequality that, you know, yeah, that's the thing you're missing, so just violate the non-equality. Okay, yeah, so that's showing that non-real representability is not polynomial simplifiable. Last thing is, first thing I should mention, the real representability is not finitely axiomatizable, I should say, even assuming complex representability. Okay. So for this, for odd n, we'll have a matroid sort of encoding x is not y, but x to the n is z on a line. And now to compare m sub n and m sub n for distinct sort of odd n and m. If we have a matroid m that encodes z equals y to the n on this line, then if we have the amalgam where we've glued these two matroids on the line L, we have that n with the amalgam with sort of our first matroid m sub n encodes z having two distinct nth roots, whereas the latter encodes that the n and mth root of z are distinct, which is just true of the reals. But the former is only true, or is only possible over complex numbers. So the former is sort of complex representable, but not real representable. Well, the latter is both real and complex. So yeah, the key idea here is that, well, yeah, z for odd n, z only has one nth root. So the result of this is that we have an infinite list of matroids that we can distinguish with amalgams across L and real representability. Because if I have two of these matroids, can pick an n and do the amalgam, and one could potentially, or yeah, if we chose n correctly, one's going to be real representable and the other is not. So we have an infinite list that can be sort of distinguished into different, you know, using sort of information communicated across sort of a line L. And if you knew My Hill and Road or Brussels, this should be familiar. And the idea is that can construct sort of a generalized sort of truth table to communicate all the information of the matroid on the line L. So everything you could care about in the matroid, like that you can access from an amalgam, you can communicate just by looking at a truth table of that sort of determines whether or not an amalgam should be true or not. Yeah, in some sense it's texture sentences as well from since we texture. And you can show just because there's finitely many cases or finitely many things we know about making with each step, like in our logic, there's only finitely many generalized truth tables. So it's impossible to have such a list if real representability had a sentence. Because if we had a sentence, we could just use the generalized truth table to determine validity. So yeah, this is also impossible. Okay, so yeah, these are sort of what we now have. Everything that sort of went bad for matroids in general still goes bad for complex representable matroids. And can sort of maybe ask other questions, like what if we now consider characterizing real representability for matroids where we know that there's a complex representation that only sort of has a bound number of complex entries, because all the constructions we had sort of needed a whole bunch of complex values on.
When you say complex entries, you mean non-real entries?
Yes, I mean, yes, exactly.
Okay.
Yes. Yeah, non-real entries. Or if you know what the complex representation is, and you know it is a complex, if you can, yeah, that's really good. I mean that's a different problem, but you know, same vein. If you have more access to the complex representation, or you know special criteria.
So when you say it has a bounded number of
So
we're just guaranteed that if it's real representable, it can be represented with a bounded number of entries, or we get the entries? Or
no.
what's-
I'm just asking, well, it already went bad, so what if we know, this is like a stronger thing, what if we know it's almost real, it almost has a real representation? This is, you know, I certainly don't think it would be true. General, I mean, yeah, things.
We know that it's complex representable, and we know that there exists some subset of 99.9% of the base elements that we can embed in the real.
Exactly, yes,
Space.
or you know, up to, yeah.
And then the question is, can we distinguish?
Yes,
Yeah, up to, yeah.
yes.
I don't know what 99.9
So,
is.
should point out the some of the constructions we had were sparse in some sense. The swirl-like things. So you can still do certain things for sparse representation. But if you have, you know, less than maybe a constant number, you should be able to sort of do something, right? Or if you know of the non-zero entries, this percent or this, you know, 99% of them are real. Yeah, so this is sort of more interesting computational setting potentially. And yeah, if you have representations, like that would be more interesting from a computational standpoint. And from a structural standpoint, sort of, we needed sort of a whole bunch of different values. If you looked, constructions needed sort of various products. So what if we don't have lines or gone lines as a minor? What can we sort of now can we sort of still can we then characterize real representability? Or for more generally, sort of, is there no uniform matrix as a minor? Well, it is. Maybe even more strongly, what if you don't have a uniform matrix in your bounded branch? What if you know have much stronger sort of information about the structure of your matrix? Yeah, so these are still sort of potentially interesting problems. And yeah, the last one is somewhat motivated by Crusoe type stuff. Okay, thank you.
Thank you. Any questions?
So I have unrelated questions. So is there a good estimate on the number of complex representable matroids over n element?
For the number, I don't. I mean, they're both two. So for representability, just like any representable matroid in general, well, I think it's 2 to the poly n. Sounds right, but I think it's either 2 to the power of the n or 2 to the power of the n times 2 to the n. I should know this. I think, yeah, 2 to the power of the n times 2 to the n is just matrix in general. But for representable matroids, it's 2 to the poly n. Yeah, no, that makes sense. Yeah, because so for complex specifically, I don't know. But
Or is a typical complex representable matrix is not really representative?
generally, like, I can't think of a proof offhand, but generally, no, it certainly shouldn't be.
Didn't you already prove that almost all?
Yeah, right.
Yeah.
Yeah, you're right. Exactly. Yeah, no, it is.
So what is
Like almost all complex representative matroid are not real representative. Is that
Well, depends how you're counting it, right? If you're counting on the number of elements. So you do have that every sort of any minimal complex representable matroid that isn't real representable, every real representable matroid is contained in a complex representable matroid that's minimal, not real. So, I don't know. So the question, one interesting question is sort of still excluded minors on n elements versus the number of real representable matroids in elements. Making them in matroid characteristics. But generally, I'd say fairly confidently that.
But almost all versus the difference between 2 to the poly n versus 2 to the 2 to the n. It's like almost all is a pretty weak. In this
2 to the 2 to the n is for all matroids.
Yeah,
2 to the poly n.
poly n is for representable matroids.
Yeah.
Still, it's pretty easy to get. I feel it's pretty easy to get.
So yeah, it should certainly.
is there some study for rational representative matroid representative or rational field? Are they very much different from real representative matroid?
So this was one thing we were also sort of thinking about, but then using von Stout stuff, you can encode polynomials, right? You have an addition and you have multiplication sort of gadget that you can use to encode sort of polynomials. So you can encode one of the von Stout have been used in matroid theory almost essentially a year after matroids were introduced by Whitney, and McLean cited Whitney, and he constructed a matroid that requires it to exist a root of 2.
Okay.
But
okay.
if you could decide whether a given matroid that is real representable is rational representable, then you could decide whether sort of polynomial has a rational root, which is open. So just decidability of rational representation is it's not known whether it's decidable. Real representable is at least decidable.
So do you also have the result like almost all real representable matroids are not rational representable? Probably that is. Like you have a real and complex, but now like a rational and real.
For asymptotics, I would expect just because you can have things go badly in sort of small places. Yeah, it should. Although comparatively, if you're looking at, if you're looking at, so the same paper Peter Nelson talks about, asymptotically almost all matroids are not real representable. He has sort of conjecture regarding sort of what do most representable matrices look like asymptotically. And I believe most matroids asymptotically should just be representable over all infinite fields. I need to check this, but I think essentially just because to almost all matroids that are representable don't sort of have any or too many incidences. So I'm pretty sure it would be equivalent to, almost all representable matroids are representable over all infinite fields. I don't know. I think that sounds, yeah. So in that case, that would be, that would, yeah, I don't think